Welcome back to the wonderful world of physics. This is Physics 102A, the Chapter 5 homework solutions on work and energy. We start with number 29. You push a heavy box applying a 540 Newton horizontal force in the direction of motion while the box slides 3.5 meters across the floor. How much work do you do? All right, just a simple one-dimensional problem. Here I've drawn the vectors of force and displacement. They're in the same direction. We're going to use the equation that work is force times displacement times the cosine of the angle between them. Now, since they're going in the same direction, that angle is 0 degrees. Cosine of 0 is 1. So we have 540 newtons times 3.5 meters, and we get 1890 joules of work. Number 31. A 1320 kilogram car moves in the positive x direction with speed 21.5 meters per second, assuming constant braking and drag forces. Find the force and the work needed to stop the car in a distance of 145 meters. All right, let's first write out the given information. We have V naught and V. We have the mass, we have the displacement. And the question is asking the force and the work needed. I've done these in opposite order, and so I've done the work needed. That seems to be the easier one if we remember the work energy theorem, because work is change in kinetic energy. So we have the final kinetic energy, and because it's at rest, that goes to 0, minus initial kinetic energy, 1/2 mv naught squared. And so we get negative 305,000 joules. Now, it's negative. We expect it to be negative because if a force is hindering motion, meaning slowing it down or bringing it to rest, it's going to do negative work. Once we have that answer, let's do question A. I've drawn the force diagram, the delta x displacement. I'm sorry, not the force diagram, the force vector and the displacement vector. You can see they're opposite each other. That's going to give a cosine of 180 degrees. And we'll once again use the formula that work is force times displacement times cosine theta. So force is work over displacement cosine theta, and we get 2104 newtons. Now, the question asked, what is the force? I've more solved for the magnitude. The book's answer says negative 2104, which just means it's in the opposite direction of displacement. An alternate solution for number 31 is to do part A first. So we could do the kinematics, solve using kinematic equations for acceleration. We get negative 1.594 meters per second squared, and then F equals ma, and there's the negative 2104 newtons. Then do part B. Work is the force times displacement times cosine theta. Now, for that equation, we're going to always use the positive value of force, and so that'll give us negative work. Number 33, a 1.52 kilogram book slides 1.24 meters along a level surface. Coefficient of friction between book and surface is 0.140. Find the work done by the friction. So I've written out the given information. I'll draw a diagram. We have friction going one way, displacement going the other way. Work is friction force times displacement times the cosine of that 180 degrees that's between them. Remember that kinetic friction is mu sub k times mg, mg being the normal force. And then we have times displacement, and the cosine becomes negative 1, so we get negative 2.59 joules. Number 35, a force given, you can see at the top, is applied to a cement block on a level floor. Find the work done by this force if the block's displacement is, and we have 3 different scenarios here. One of them is completely in the I-hat direction. The next is completely in the negative I-hat direction. And the third scenario is equally in the I-hat and J-hat direction. All right, so It is appropriate when we have multi-dimensional motion. We're given the x and y components of displacement. This is a really easy formula to use. Work equals the x component of force times x displacement plus y component of force times y displacement. And so when we do that for scenario A, where the vector is 2.5 and 0, we multiply the x components and then add the multiplication of the y components, we get 5.85 joules. If we do scenario B, we can do the same thing, but now the x is negative. We get negative 5.85 joules. And finally, in scenario C, once again, we multiply the x components between force and displacement, and then add the y components between force and displacement, and we get 8.5 joules. Number 45. If 13.4 joules of work compress a spring 2.37 centimeters, what is the spring constant? Okay, we'll write out the given information. Let's get it in MKS units. Work is 1/2 kx squared. Let's solve that algebraically for k. So k is 2 times work over x squared. We'll plug in those values and we get 4.77 times 10 to the 4th newtons per meter. Number 47, find the work done in extending a spring with k equals 150 newtons per meter from 0.1 meters to 0.3 meters. It's appropriate to use this general equation for the work done of a spring. It's 1/2 k times the final displacement squared minus 1/2 k times the initial displacement squared. You can factor out the 1/2 k. So we have 1/2 times 150 newtons per meter times the difference of 0.3 squared and 0.1 squared. And that gives us 6 joules. Number 57, a boulder flies through the air at 12.4 meters per second with kinetic energy 305 joules. What is its mass? And then, parts B and C, what is the boulder's kinetic energy if its speed doubles or is halved? All right, let's look at part A after I've written out the given information. Remember that kinetic energy is 1/2 mv squared. So solving algebraically for mass, that's twice the kinetic energy divided by v squared. Plug those values in, first making sure that they're all in proper MKS units. They are. So we get 3.97 joules. Now, there's a variety of ways to do parts B and C. Here's how I've chosen to do it. We recognize that kinetic energy, and I have a subscript 2 for the second scenario, is 1/2 mv2 squared. And it says the speed doubles. And so let's substitute for v2. Let's make it 2v1. Now, another way we could do this, just as a side note, is actually to go up to the top, double the speed, and do 24.8 meters per second. But this way keeps it more general. And so let's just keep going on this way. So simplifying all this, we have 1/2 m4v1 squared. Now, if we move the 4 out to the left, we recognize that that's 4 times 1/2 mv1 squared. So it's 4 times the answer, or 4 times the original kinetic energy, 4 times 305, and that gives 1220 joules. Now again, you could have you didn't have to go through this algebra and substituting. You could have just doubled the original velocity, plugged it in there. But here, I like this solution because it shows you directly that the kinetic energy, when the speed is doubled, the kinetic energy is 4 times what it originally was. Now for part C, we're going to cut in half the original speed. So 1/2 mv squared becomes, notice I've substituted in for the velocity 1/2 of v1. And so the v1 gets squared, but also the 1/2 gets squared. And that 1/2 getting squared becomes 1/4. Let's move it out to the side. And so here you can see that the new kinetic energy is 1/4 of what it originally was. So 1/4 of 305 joules, or about 76 joules. Number 67. If a 25-gram bullet with a speed of 310 meters per second travels 15 centimeters into a tree before stopping, what is the average force exerted to stop the bullet? Well, we have the mass. Let's get everything in MKS units. So 0.025 kilograms. We have the initial speed. We have a final speed. I didn't bother to write it down, but the bullet's coming to rest. So final speed is 0. Displacement is 0.15 meters. And we want to know what is the force. So the work done on the bullet is the force. And here I've written the average force because, well, that's what it's asking for, average force. Also keep in mind, as it's penetrating the tree, the force is going to be changing every microsecond, but we're just looking for that average force. So work is average force times displacement. By the work energy theorem, that's the change in kinetic energy is average force times displacement. So we're going to divide both sides by delta x to get the average force. And in the numerator, change in kinetic energy is 0 minus 1/2 mass times the original velocity squared. So when we plug in the values that are up at the top of the page, we get 8,008 newtons. And we're really only allowed to use 2 significant figures for this problem. So although the book says 8,008 newtons, and that's what I've written, we should round that appropriately to 8,000 newtons. Number 74. How far must you compress a spring with K equals 650 newtons per meter in order to store 450 joules of energy? Well, the energy stored, the potential energy in a spring is 1/2 kx squared. We're going to solve that algebraically for x. So we'll multiply by 2, divide by k, and we get x is square root of 2u over k. We're going to plug those values in, and we get 1.18 meters. Number 82, at the Zero Gravity Thrill Amusement Park near Dallas, Texas, people drop from a 30-meter tower into a net below. At what speed do they reach the net? All right, good conservation of energy problem. Let's make the initial position y0 equals 0. Down at the net, it's negative 30 meters. It's got to be negative because it's got to be, since it's down, the direction that gravity pulls you, it's going to be lower than 0, so negative 30 meters. And now let's set up conservation of energy. E0 equals E1, so I'll make condition 0 be at the top, condition 1 be down at the bottom. And so we're going to write out all the relevant energies. So we have kinetic 0 plus potential 0 equals kinetic 1 plus potential 1. Now, very often in problems like this, some of these terms will go to 0. So let's think about the picture, think about the person at the top of the ride and at the bottom of the net, and see if any of these go to 0. Well, here we have at the top, the person's at rest. V0 is 0, so there is no kinetic energy. Here we have potential energy. Well, I've made the initial position be 0, so mgy0 becomes 0. So based on the position that I've made, that being 0, the person has 0 joules of energy. So the left-hand side, all zeros out. On the right-hand side, when the person hits the net, it's 1/2 mv1 squared plus mgy1. We can factor out the m, essentially dividing both sides of the equation by m, and we're left with 0 equals 1/2 v1 squared plus gy1. Let's solve for v1. We get v1 squared is negative 2gy1, and v1 is the square root of negative 2gy1. Then we'll plug in all the values. The negatives cancel out, which is good because we're about to take a square root. We don't want to take a square root of a negative number. And so we get 24.2 meters per second is the speed that the person hits. By the way, we could have done this problem back in chapter 2 when we were just dealing with kinematic equations, because we could say that the final speed squared is the initial speed squared, which is 0, plus 2 times g times delta y, or I should say 2 times acceleration times delta y. And if the person's going down, and if up is the, if we make up the positive direction, acceleration is negative g, change in height is negative 30 meters, and we're going to get the same answer, 24.2 meters per second. Number 85. A roller coaster going 19.2 meters per second starts up a hill. Ignoring friction, what is its speed after it has risen 12.2 meters vertically? So I've drawn a little picture here to the right. It's starting up a hill. It's got a certain initial speed, and we want to know what's its speed when it goes 12.2 meters higher. We'll start conservation of energy, E1 equals E2. Kinetic 1 plus potential 1 equals kinetic 2 plus potential 2. And nothing is going to zero out. Well, no, I'm sorry. Potential energy zeroes out because we're going to make this height 1, be 0. So mg times y1, that's going to go to 0. Nothing else zeroes out. So what we have left is here we have 1/2 mv1 squared equals 1/2 mv2 squared plus mg times delta y, and I could also replace that delta y with simply y2. Now we can divide both sides of the equation by m, and we're left with something that looks a lot like a kinematic equation that we learned in chapter 2. So we have v1 squared is v2 squared plus 2g delta y. And here we solve for v2. We're going to take the square root of both sides, plug those values in, we get 11.4 meters per second. And then we check the roller coaster. We know it's going to slow down because it's going uphill. It's gaining potential energy. We know it's going to lose kinetic energy. So we should check our answer and see if it seems reasonable. Has the roller coaster slowed down? Yes, it went from 19.2 to 11.4. And we should always check our answer to see if it's reasonable. Now, a common mistake I see through the years on a problem like this is students have a plus sign right in here. And then, but they should be able to catch it because in the end, if they have a plus sign instead of a minus sign, they should show the roller coaster speeding up as it goes uphill. And then that should lead them to think something is not right here and to go back and see what the mistake was. Number 86. A horizontal spring with K 75 newtons per meter has one end attached to a wall and the other end free. An 85-gram wad of putty is thrown horizontally at 3.4 meters per second directly toward the free end. Find the maximum spring compression. All right, so here's a picture I've drawn. State 1 is the wad of putty being thrown at the spring that's at equilibrium. State 2 is it's hit the spring is compressed, and it's at rest. So we'll say energy 1 equals energy 2. And I've already made things go to 0 as appropriate. Now, since all of this is happening horizontally, there's no change in height, then we can make both of the potential energies be 0. Effectively, the height of 1 is 0, the height of 2 is 0. Potential energy, gravitational, isn't going to come into play. All right, let's think about state 1. We've certainly got the kinetic energy, 1/2 mv1 squared. The spring is at equilibrium. So if we wanted to, on the left-hand side, include the spring potential energy, it would be 1/2 kx squared. But at state 1, x is 0. The spring is not compressed, and so that just goes to 0. So all we're left with on the left-hand side is kinetic energy. On the right-hand side, there's no kinetic energy because the spring has been brought to rest. The wad of putty has been brought to rest. Everything's at rest. But what we do have is a compressed spring. So the potential energy is 1/2 kx squared, where x is the compression of the spring. So we're going to take this equation, solve it for x. And when you do that, you should get square root of mv1 squared over k. You get 0.114 meters or 11.4 centimeters. Number 89. A rubber ball is dropped from rest 2.4 meters onto level ground. What is the ball's speed when it hits the ground? Bouncing back, the ball loses 25% of its mechanical energy. To what height does it rebound? All right, for part A, we could use a kinematic equation from chapter 2, but let's do better than that. Let's use conservation of energy because that's what we're studying in chapter 5. So let's draw these actual 3 conditions. State 1 is when it's at its height of 2.4 meters. State 2 is right when it's hitting the ground. State 3 is the bounce back. All right, let's answer question A first. E1 equals E2. Conservation of energy applies. So state 1, there is no kinetic energy. State 2, there is potential energy, but I'm calling the ground a height of 0, so potential energy will be 0. So what we're left with is U1 equals K2. So we have mgy, I should have written mgy1 equals 1/2 mv squared. And so we solve for v, and it's square root of 2gy. 2g times the original height, square rooted. And we get 6.86 meters per second. Now, question B, we can no longer use purely conservation of energy. We're going to use a modified conservation of energy. It says bouncing back, the ball loses 25% of its mechanical energy. So instead of saying E3 equals E1, we can say E3 is 3/4. It's 75% of E1. So it's a modified conservation of energy. 75% of energy has been conserved. So E3 is 75% or 3/4 of E1. And now let's continue from there. So E3, we had mg, I've used different variables, I'm sorry. Up here, I called it y, and I said I should have called it y1. Oh, hey, let me just, I can't edit the video. I'd like to erase the last minute and start again with part B. Okay, so E3 equals 3/4 of E1. So E3, I mixed up the variables I was looking at. We're looking at the potential energy at 3, and it doesn't have any kinetic energy because this is as high as it bounces. So we can say mg times the height of 3. And you'll note that, and this is what I was apologizing for a minute ago, up in part A, I was using the variable y. Now I'm using h. Sorry about that. They're the same thing. Okay, equals 3/4 of E1. So that's going to be 3/4 of mg times the height 1. And that's actually the same as this mgy, which I should have said mgy1. I've just gone to using h's. So 3/4 mgh1. Now let's simplify this. Well, the m's and the g's can divide out, and we're left with height of 3 equals 3/4 of height of 1. So interestingly, the result we get is that if it's 75% of the original energy, then it's 75% of the original height. And that sounds reasonable because its energy at conditions 1 and 3 is purely potential energy, and potential energy is proportional to height. So it's only coming up 3/4 its original height, and that is 1.8 meters. Number 98. What power is needed to lift a 350 kilogram crate of bricks from the ground to the top of a 23.8 meter high building in 1 minute? So you know that power has to do with work and time. Power actually is work divided by time. If we're lifting this load, the work we do is mg times the height that we lift it. We could also say mg times delta y. Let's plug all this in. 350 kilograms times 9.8 newtons per kilogram times 23.8 meters. That numerator is the work done. And now we're going to divide it by the time. It says in 1 minute, but let's get this in seconds so we can express our joules per seconds as watts. And we get a power of 1361 watts. Number 99. Find the work done by a motor operating at a constant 8.5 kilowatts for 30 seconds. Well, we'll use the same equation, but now we're solving for watts. So we're solving for work. So work is power times time. 8.5 kilowatts, let's get that in watts. So 8,500 watts times 30 seconds, and that gives us a total work of 255,000 joules. And that is the end of the Chapter 5 homework. Have a great day.